Let's try to solve example 6.6. In the following pairs of halogen compounds, which would undergo SN2 reaction faster. First of all, identify the type of halogen, whether it is primary, secondary or tertiary. The carbon to which halogen is bonded is the alpha carbon. Here the alpha carbon is this alpha carbon. In the first structure, this alpha carbon is bonded to just another carbon. So the first halogen compound is the primary alkyl halide. In the second structure, the alpha carbon is bonded to another two carbons. So that's why it is secondary alkyl halide. And we know for SN2 reaction mechanism, primary alkyl halide react faster than secondary alkyl halide. So the first structure will undergo faster SN2 reaction mechanism. In the second pair, here they both are primary alkyl halide. But in the first alkyl halide, the halogen is iodine. And in the second alkyl halide, the halogen is chlorine. And we know longer the bonds are easier to break. Here the bond is formed between carbon and iodine. And in the other case, bond is formed between carbon and chlorine. As the iodine is bigger than chlorine, the bond length between carbon and iodine is bigger, and bigger bonds are easier to break. So that's why it is easier to cleave the bond between carbon and iodine. And in the second point, when iodine leaves the molecule, it will leave as I negative ion. And in case of chlorine, when chlorine leaves the molecule, it will leave in the form of Cl negative ion. As the iodine is a bigger, it can accommodate negative charge better than the chlorine. So that's why I negative is a good leaving group. It's a good leaving group. So that's why also alkyl iodide react faster under SN2 reaction mechanism as compared to alkyl chloride. Now come to the next question. Predict the order of reactivity of the following compounds in SN1 and in SN2 reactions. The four isomeric bromobutanes. So let's draw the structure of bromobutanes. First of all, we can draw normal bromobutane. So here there are 4 carbons, CH3, CH2, CH2, CH2 and Br. So this is N-bromobutane. Now draw isobromobutane. So here we can draw CH3, C, H, CH2 and here this is bromine and here this is CH3. So this is isobromobutane. Now draw tertiary bromobutane. So here we can draw CH3, 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 Br. So this is tertiary bromobutane. Now we can change the position of bromine. So here we can draw Br2 at second position. So here we can draw Br at second position. CH2, CH, CH3 and here when I attach Br. So it will become 2-bromobutane. So these are the 4 isomers of bromobutane. This is first, second, third and this is the fourth one. Now let's predict the order of reactivity for SN1. For SN1 we know tertiary alkyl halide react faster. Identify the type of alkyl halide first. Here bromine is bonded to this carbon. So this carbon is the alpha carbon and this alpha carbon is the primary alpha carbon. So this is primary. That means bromobutane is primary alkyl halide. Here this is the alpha carbon and it is bonded to just another one carbon. So this is again primary alkyl halide. And here this is the alpha carbon and it is bonded to 3 other carbons. So that's why this is tertiary alkyl halide. And in the fourth structure, This is the alpha carbon and it is bonded to another carbon. So that's why this is secondary alkyl halide. For SN1 reaction, reactivity of molecule is directly proportional to the stability of formed carbocation. So I can write here SN1 reaction is directly proportional to the stability of carbocation. Stability of carbocation. Now let's examine these isomers. When this bromine leaves the molecule in the form of Br negative ion, positive charge will develop at alpha position, and this will be the primary carbocation. This primary carbocation will get stabilized by the plus I effect of propyl group. In the second isomer, when this Br leaves the molecule in the form of Br negative ion, positive charge will develop at the alpha position, and this is again the primary carbocation. This is again primary carbocation. But when you compare both the primary carbocations, which one will be more stable? In first primary carbocation, there is plus I effect of propyl group, and in the second carbocation, the plus I effect of isopropyl group. The plus I of isopropyl is stronger than the normal propyl group. So the primary carbocation, which is formed in case of second isomer, is more stable carbocation formed in case of first isomer. So this is more stable. In the third isomer, this Br will leave the molecule in the form of Br negative and positive charge will develop at the alpha carbon. And this alpha carbon is bonded to 3 other carbons. So this is tertiary carbocation. And in the fourth isomer, when this Br leaves the molecule, positive charge will develop at the secondary carbon. So this will result in the formation of secondary carbocation. And we know tertiary carbocation react faster than the secondary and primary react least. So here when you arrange them in the increasing order, of reactivity in SN1 reaction mechanism, you will see first isomer will react least, then the second one, then fourth isomer, and here then the third isomer will react fastest under SN1 reaction mechanism as it results in the formation of tertiary carbocation. Now predict the order of reactivity for SN2 reaction mechanism. We know for SN2 reaction mechanism, less crowded molecules react faster. Means the primary alkyl halide will react faster under SN2 reaction mechanism. So for SN2 reaction mechanism, the first isomer will react fastest, then the second isomer, then the fourth one, and then the third isomer. Because third isomer is more crowded than the fourth isomer. So that's why this will be the order of reactivity for SN2 reaction mechanism. Now let's try to solve the second question. First of all, draw the structure of the given molecules. So let's try to draw the structure of given molecules. Here this is C6H5C. C6H5 is phenyl group. Here this is bonded to CH2 and it is bonded to Br. In the second structure, again phenyl group is there. It is bonded to CH and CH is bonded to again next phenyl group. And here it is bonded to Br. In the third structure, again phenyl group is there. And this phenyl group is bonded to CH. CH is bonded to CH3 and here it is bonded to Br. And in the fourth structure, there is again phenyl group. It is bonded to carbon and here one side it is bonded to Br, other side it is bonded to CH3 and on the other side it is bonded to phenyl group. First of all, categorize them as primary, secondary and tertiary. Here this is the alpha carbon and it is bonded to one carbon. So this is the primary alkyl halide. Here this alpha carbon is bonded to another two carbons. So that's why this is secondary alkyl halide. Here this alpha carbon is bonded to another two carbons. So again this is secondary alkyl halide. And here in the third structure, this alpha carbon is bonded to another three carbons. So this is tertiary alkyl halide. For SN1 reaction, first of all, for SN1 reaction, identify the type of carbocation is formed. Here when this Br leaves the molecule in the form of Br negative, positive charge will develop at this carbon and this carbon will result in the formation of primary carbocation. And this primary carbocation will get electron density from the benzene ring. In the second structure, this result in the formation of secondary carbocation. So here it will form secondary carbocation. In the third structure, when Br leaves the molecule in the form of Br negative, it results in the formation of secondary carbocation. And in the third, it results in the formation of tertiary carbocation. Here we get two secondary carbocation. First of all, identify which one will be more stable. In case of second compound, there are two benzene rings bonded to formed carbocation. So because of the resonance or plus R effect of these two benzene rings, this carbocation will be more stable as compared to the other secondary carbocation. So this will be more stable than the secondary carbocation formed by the third molecule. So when you arrange them in the increasing order of reactivity for SN1, now I will number these molecules 1, 2, 3 and this is 4. For SN1, fourth will undergo faster SN1 reaction as it results in the formation of tertiary carbocation. So fourth will undergo faster SN1. Then the second will undergo faster SN1 than the third and first comes at the last. Now let's arrange these molecules for reactivity of SN2 reaction mechanism. We know less crowded molecules react faster. So here among all these molecules, the first one is the least crowded. So first one reacts fastest under SN2 reaction mechanism. Then when you compare between 2 and 3, in 2 there are two benzene rings which makes the molecule sterically crowded. But here in the third isomer there is one methyl group which makes the molecule less crowded. So the third compound will be less crowded. As it is less crowded, it will undergo faster SN2 reaction mechanism. So third comes first, then the second and fourth react least under SN2 reaction mechanism as it is the most crowded one.